I'm going to give you guys a basic primer on knife steel. A lot of us know that we want the best knife steel possible, but at the same time, we don't even know what that is. We don't even know what steel is. We do know that we want fine grain structure. We know that we want the ease of sharpening, the toughness, this and that. But what is a steel? Nobody even knows what it looks like, or, you know, whenever you look it up, it's so complex, or it only kind of applies to the industry, and you're like, you know what, I want to know how that applies to knives, but I just get a nosebleed whenever I read about it. So with this video, I'm going to break it down as simply as possible. What is steel pertaining to knives? So you see right here, forgive my art skills, but here I have different structures right here. And this is to help you guys visualize what steel is, because a lot of people, they'll tell you steel is a crystal structure. And you think in your head, like, okay, what do we got, like a diamond sword? Is it just made out of one crystal, or how does that all work? Well, here I've got several different crystalline structures. And so this right over here is crystalline. You can see how even and road it is over here. And this is supposed to be amorphous. It has kind of no shape to it. What metal or iron steel is it's polycrystalline. Which means that it's made up or composed of several crystals, all growing independently with each other until they basically run into the adjacent crystal. So knife steel is made out of several crystals. It's polycrystalline. Also, you can't talk about steel without first understanding what steel is, because the most important thing for steel is actually iron. Steel is iron, and to be exact, it's actually an alloy of it. So depending on how much carbon you add to iron determines what the steel is going to do. You get several different mechanical properties depending on how much carbon you add. So anything from basically 0.03% carbon all the way up to, let's say, about 2% carbon. This is the range that makes steel. And for knife steels in particular, you probably want something around this or up to this is kind of the limit for a traditional knife steel. So really, we're talking about a very specific range of carbon, and we'll get into what the carbon does in different amounts in another video, but this is just a very, very rudimentary video about it. So basically anything past this, we're back to a type of iron, and anything past 2%, technically, you're back to what's called a cast iron. You have to understand what's amazing about iron and why iron is important for how it makes steel is iron basically has two different shapes that it takes depending on what heat it's at. At room temperature, it's what's called body-centered cubic. So we have basically a square right here, and you can see there's an iron atom in the middle. So you would see a giant rows and rows and rows of all these. These are iron atoms right here. This is an iron atom as well. Just the iron atom is in the middle of this kind of cubic structure. Think of a six-sided dice, and there's an iron atom in the middle of that dice.
We have the body-centered cubic. We have an iron atom in the middle, and then an iron atom at each corner. And if we zoom out, you could see kind of what that structure looks like. And this wouldn't be a perfect square the ends of this structure would be all, you know, different shapes or whatnot as it runs into the other ones, and that would form that grain boundary. But that's kind of an idea of what that looks like, pretty trippy. And then we can go back. So this is body-centered cubic. There's an iron atom in the middle, less spots for the carbon to attach to.
When you heat the material up past a certain critical temperature, then basically all those atoms shift. They shift so that there's an iron atom at the face of every side of the cube. So basically that becomes face-centered cubic because each iron atom takes place at the face of each side of the cube. So all the basically atoms arrange themselves in a very interesting pattern where there's an iron atom at the face of each side of the cube.
Here, and you notice the difference is that we have an iron atom at each face of the cube here. Okay, so that's actually more spots for the carbon to attach to so that the steel can actually be hardened. And if we zoom out here, you can see that basically it's the same thing, it's just that all the iron atoms are more compacted now. Alright, so the heat has caused them, once they get to that critical temperature, to kind of all shift over to the right or the left. And so now we have a much more compacted structure. But this allows more spots for the carbon to basically seep into like a sponge, which then allows the steel to be hardened. So here we have it. This is face-centered cubic. There's an iron atom at each face of the cube.
That opens up more spots for the carbon to actually get in there. More spots on there. Once the carbon gets in there, then that's when something very, very interesting happens. When it's cooled rapidly, faster than the carbon can escape, then each one of those structures changes shape. It distorts to what's called body-centered, because we still have an iron atom in the middle, tetragonal. It cools faster than basically the carbon can escape from this molecule right here. And so what that does is it makes a very, very hard structure called Martensite, or that's what gives steel its strength. You always hear people talk about heat treating of steel, or it's got to be heat treated, or this and that, heat treated. Well, this is what gives steel its hardness, in that we open up more spots for the carbon to get in there, we soak the carbon inside there, and then when we cool it too fast, faster than the carbon can escape, that's what builds those needle-like structures called Martensite that then allows the blade to be hardened. You see over here, putting everything kind of together, we've got a knife right here. We've learned that basically we have a knife, it's made up of grain. There's a grain to it, it's polycrystalline, maybe just different kinds of shapes or whatnot with boundaries. They're all growing until they run into the next one. We also learned that, and inside each grain, the grain can basically kind of grow and shrink. We'll get into that. That's a little bit more advanced depending on how well it's actually been heat treated, and we want the finest grain possible, so there's a lot of factors that go into that. But each grain is made up of rows of organized atoms, and depending on what the temperatures were and how much carbon's inside the steel will determine how hardenable it is and how it gets hard and things like that. And then we have the Martensite right here. And so this being a knife steel right here, the Martensite inside the grain would look like this. A lot of different needle-like structures, almost like hay, inside each one right here. So it'll be made up of a lot of those. And then what people also think of is what's called carbides. Some of those, the really fine ones, are dispersed throughout the Martensite, but a lot of them end up here at the grain boundary, especially when we talk about more alloyed steels that have other alloys like chromium, things like that. Then they start to take up spots at the actual grain boundary because they're just too large to move through basically the steel matrix. You know, something like carbon can diffuse really well because of its size relationship with the iron. It can move around a lot more, and then something like chromium is a lot larger, so it can't really move through the iron matrix that well. But that's kind of it in a nutshell. I mean, I really only scraped the surface on this for you guys. I hope that helped. If not, we'll try to think of a simpler way to explain to you guys how this works. Alright guys, thanks for watching. Take care.